So what is induction? Ash, can you present this?
Yeah, so a mathematical induction is a common proof technique that can be applied to all areas of mathematics. So today we will cover algebra-oriented induction and how it can be used for algebra, but it can be used for most types of contest problems. The main purpose of mathematical induction is to prove that the proposition Pn, which you call Pn, is true for some positive integer n. It is used to prove that something is true for every natural number. So, uh, for example, proving 1 plus 2 plus 3 plus all the way up to n is equal to n times n plus 1 over 2 is positive for all positive integers n. So because of the fact that it has the term for all positive integers, so it's worth using induction. So induction, you can use induction as a technique to prove stuff when you have something over positive integers. Yeah, so basically induction works on the basis that the proposition for the numbers leading up to n work to prove that Pn works. That is the proposition for that works for n is true given that it works up to n. So a simple way to do this is to prove that Pn is prove the proposition for a base case, and that is like a very small number for which you can easily check that the statement is true, and then assume that the proposition works up to some arbitrary positive integer n, and you use that assumption to prove that Pn is true for Pn works for n, to prove that Pn plus 1 works for n plus 1. So this way, well, if we prove the base case A is true, then we can use Pn being true to prove that so the Pn to prove Pn plus 1, so that the proposition is true for n plus 1. Yep, so from this that means if P of A plus 1 is true, so P of A is 2, and then so on we have for any arbitrarily large natural number. So we basically know that the proposition is true for all natural numbers or all positive integers. Yep, so I'll get Alan.
Okay, so now we'll have an example using induction, although this problem doesn't involve it. Like you can do it without induction, but it's a case where it makes the induction pretty clear. So I'll give you guys 30 seconds to try to figure it out. Okay, does anyone have any idea on how to do this? Can you guys tell me in chat? Okay. So for the base case, what would be an easy base case to choose? It would be n equals 1, right? Because that's just 1 over 2 equals 1 over 2, or equals 1 minus 1 over 2. Okay, and what's the assumption? The assumption would be to choose, like, for some k, suppose the problem statement holds. Or in other words, 1 over 1 times 2 plus all the way to 1 over k times k plus 1 equals to 1 minus 1 over k plus 1. So how do we get from this to the next one? to k plus 1? Well, first we look at the k plus 1 statement. The k plus 1 statement would be the same thing as this, but then we have to add the 1 over k plus 1 times k plus 2 on both sides, right? If k plus 1 was true from k. Does everyone agree? If you don't agree, you can tell me in chat. Okay, but what's negative of 1 over k plus 1 minus 1 over k plus 1 times k plus 2? What's that equal to? That's equal to, so if we look at the right-hand side, it's equal to 1 minus 1 over k plus 1 minus this expression is just 1 over k plus 1 minus 1 over k plus 2. You can verify that by doing 1 over, that would add up to k plus 2 minus k plus 1 all over k plus 1 times k plus 2. Is this thing? So it's the same thing as taking away k plus 1 and then adding on, because negative times minus is adding something, 1 over k plus 2. And what does this cancel out to? This is 1 over k plus 2. So we see that the k plus 1 case holds. And because of the base case, n equals 1 holding, we know that n equals 2 holds, n equals 3 holds, and all positive integers n hold. So we know that this problem statement is true. So that's the example, and we'll do another example. Prove for all positive integers n that the sum of the consecutive odd numbers until 2n minus 1 is equivalent to n squared. I'll give you guys 1 minute to do this problem. So for this problem, you just need to try to keep in mind the steps of induction. It's the base case, and then assumption for n, and then using the assumption for n to prove n plus 1. Okay, can someone tell me a base case that we can use? Just tell me in chat. Okay, we can use the base case of n equals 1. We know that 1 equals 1 squared. So the base case is pretty trivial. And then for the assumption, we just assume this is true for some k, right? And then for k plus 1, we just need to add on 2k plus 1, right? Because 2k plus 1 equals 2 times k plus 1 minus 1, which is this thing for k plus 1. So we just need to add on 2k plus 1 onto both sides, and then we're left with the sum of consecutive odd numbers from 1 through to 2k plus 1. It's the same thing as k squared plus 2k plus 1, which is the same thing as k plus 1 squared. Right? So it holds for k plus 1 by our assumption for k. So because we proved the base case earlier, we know that 1 works, 2 works, 3 works, dot, dot, dot. So can Ash present this?
Yeah. Up until now, both the examples that Alan showed had an equality, but induction is not just limited to being helpful in proving equalities. You can also get good in like bounding or like using inequalities using induction. So, for example, he's an example is to prove 2 to the power of n is greater than n for all positive integers n. So, first of all, uh, I'll let Alan go through the example, and I'll give you a few seconds to just think about this.
Okay, so first of all, we need to find the base case, right? So what's an easy base case that we can use? Can someone tell me in chat? An easy base case we can use is the base case we've always been using, which is just n equals 1. Obviously, we know that 2 to the power of 1 is larger than 1, right? Because this is 2 larger than 1. So now we make the inductive assumption or inductive hypothesis. Oh yeah, the assumption is called the inductive hypothesis of 2 to the power of k being larger than k for some arbitrary positive integer k larger than 1. So now we need to prove the case, prove the proposition for k plus 1. So we need to prove that 2 to the power of k plus 1 is larger than k plus 1. But we know that 2 to the power of k plus 1 is the same thing as 2 to the power of k, and then times 2, right? Which is obviously larger than 2 to the power of k for integers k larger than 1. And before we made the assumption that 2 to the power of k is larger than k, so 2 to the power of k is larger or equal to k plus 1, since k is an integer. Is everyone following? Okay. And then because we know that 2 to the power of k is smaller than 2 to the power of k plus 1, we can make this inequality that 2 to the power of k plus 1 is larger than 2 to the power of k, which is larger than or equal to k plus 1. So it works for k plus 1 if it works for k, and by our base case, it works for all positive integers n. Can Ash present this slide?
Oh yeah, so the motivation for induction comes from the Peano's induction axiom. So it is a corollary of the Peano induction axiom. So let's say one is in some set S, and then for n being an element of that set, we have. So what this means is that the set would be the positive integers or the natural numbers. So this is equivalent to the form of induction, which Alan has previously covered. So yeah, if you build up from 1 and add every other number up from there, you end up with all the natural numbers. Just bad. That's how you get induction. So yeah, that's basically what we're doing, we can assume induction to be a type of ladder. And then when we reach the first rung of the ladder, you can always reach the second rung. Uh, and then after that, you can also always reach the one above. And therefore, applying the same method again and again, you can reach up as high as you want to on that ladder, which would be the positive uh, integers in this case.
So now we'll go through example problems. I'll give you guys 1 minute to try the first problem. Although these problems don't necessarily need to be done by induction, it's probably faster to do the second two by induction, but the first one can be done by pairing as well. Okay, I will now go through the proof for the first problem. So what would be the base case? Can someone tell me in chat? Okay, I'll choose the base case of 2 this time. Wait, no, that takes too long. N equals 1 and then n equals 2. So n equals 1 tells us 1 equals 1. And then we can do another base case of n equals 2, which tells us 1 plus 2 equals 2 times 3 over 2, which is just the same thing as 3. And then for the inductive hypothesis, we assume this is true for some k, right? But then how do we extend this to k plus 1? So we first look at the statement for k plus 1 if k plus 1 were to be true. And the statement would be to prove that 1 plus 2 plus 3 plus dot 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 plus k plus 1 equals k plus 1 times k plus 2. But then by our inductive hypothesis, after we add k plus 1 to both sides, what happens? So k plus 1 is the same thing as 2k plus 2 divided by 2, right? And then if we add it to this thing would equal k squared plus k. And then we also add plus 2k plus 2. So if we look at the right-hand side, it equates to k squared plus 3k plus 2 divided by 2, which is equal to k plus 1 times k plus 2 divided by 2, which is what we want. So by extending our inductive hypothesis to k plus 1, we've proved the case for k plus 1. And now we'll do the second problem. Prove that 1 squared plus 2 squared plus dot 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 plus n squared equals to n times n plus 1 times 2n plus 1 divided by 6 for all positive integers n using induction. So for this problem, you probably need to use induction, but then there's probably a method where you don't need to use induction. So it's the same thing as before, just base case, inductive hypothesis, and then extend to k plus 1. I'll give you guys 1 minute to do this. So what's the base case we can use for this problem? Can someone tell me in chat? Please tell me the base case that we can use. Okay, never mind. So for the base case, I'll just use n equals 1 again. So by n equals 1, we have that 1 squared equals 2. 1 times 2 times 3 divided by 6, right? This is obviously true because 1 equals 1. And then now we have to move on and make our inductive hypothesis. What would our inductive hypothesis be? It would be that this is true for some k. We don't need to know what k is. We just know that it's true for some k and k is arbitrary. So how do we extend this to k plus 1? We use the same method as before, right? Because these two problems are basically identical. So first we look at what k plus 1 needs us to have, and then we try to extend our hypothesis to match what k plus 1 wants us to have. So for k plus 1, we need this sum of consecutive squares to equal k plus 1 times k plus 2 times 2k plus 3 over 6. And once we add k plus 1 onto both sides, what do we have? We would get basically the same process as before, except this time it's more expanded. And you guys can verify this if you want, but just know that this is true. So because we know the base case is true and we can extend all k to k plus 1, we know that this is true for all positive integers n. And then I'll give you guys 30 seconds to do the last question to prove the sum of consecutive cubes is the same thing as the sum of consecutive positive integers squared. So when you first look at this, it looks very complex, right? Because we got the sum of cubes on one side, and we got the sum of consecutive numbers on the other side, which just makes a lot of terms. So it's very hard to work with. But if you remember what we did earlier, we found out that the sum of consecutive numbers is the same thing as n times n plus 1 divided by 2. We can just replace this part with this. So the real problem is to prove that the sum of consecutive cubes is equal to n times n plus 1 over 2. So why would it be hard to work with what we had before? Because what we had before, we had different powers on either side. Over here, it was powers of 2, and over here, it was powers of 3. So that would be very hard to work with. Which is why we want this side to just become like an expression that we can, it's just a constant expression. And then this side is sum of cubes. Okay, so for the base case, we can use anything that's small. I'll skip it. And then the assumption would just be this. And then after that, we can just expand it. We can expand the right-hand side, and then we can add n plus 1 cubed to extend our hypothesis to n plus 1. So now we've discovered that induction is very helpful for proving the sum of a sequence, the sum of consecutive numbers, sum of consecutive squares, and sum of consecutive cubes. But then it can also be extended to higher powers. So now we'll cover an alternate form of induction known as strong induction. Ash will present this.
Yeah. So, so what is strong induction? So in induction, that's normal induction, we prove a base case, and we also first prove so similarly in strong induction, we also need to prove a base case from where we start working. But like basically it's an inductive ladder, but there is no first rung to climb, so you climb nothing. Okay, if you don't have a base case, that is. So however, yeah, if you then you don't have nothing to work off. Yeah, if you do not prove a base case, so first you need to prove a base case. However, the difference between basic induction and strong induction is that instead of assuming the proposition holds for n, prove that it holds for n plus 1, we assume that the proposition holds for the base case plus 1, all the way up to n, and then we use that entire information to prove that the proposition holds for n plus 1. So the only difference being, instead of going just from n to n plus 1, you use the entire a to n to go to n plus 1 in strong induction. Yeah, so why does this still work? The reason why strong induction still works is because after we prove the base case, which we written a, and we prove that if the proposition holds for a plus 1 all the way up to n, then it is sufficient to prove that the proposition holds for n plus 1, because we have proved that it works for a, then we know it works for a plus 1. If a and a plus 1 works, then it works for a plus 2, and then so on up to n. So this would work for any arbitrary large integer n. Yeah, so here I'll have Alan going over the example.
So our example is to prove that every positive integer can be expressed as a unique sum of distinct powers of 2, which is basically that binary works. So how should we approach this problem with strong induction? And what is special about the last digit of a binary number? Can someone tell me in chat? So the last digit of a binary number is either 0 or 1. And why is this special? Okay, firstly, does everyone know what binary is? Can someone tell me what 5 from decimal would be in binary? Yeah, that's right. It is used in ASCII convention. So basically, binary is 5 in decimal, which is the number system that we usually use, would be 101 in binary, because it's just the same thing as 2 to the power of 2 plus, 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 1 times 2 to the power of 0, which is just 4 plus 1. Because if you look at a number in decimal, say 112, that's just the same thing as 1 times 10 to the power of 2 plus 1 times 10 to the power of 1 plus 2 times 10 to the power of 0. So it's basically just turning these powers of 10 into powers of 2. So each digit, instead of ranging from 0 through 9, it would just be 0 to 1. So it's either 0 or 1. Okay, so an observation is that the last digit is either 0 or 1, which means that we have a string of ones and zeros followed by 0, which is the same thing as 2k in decimal form. Does everyone understand? Because if it ends in a 0, that means it's 0 times 2 to the power of 1. That means there's something in front which all has 2 to the power of x, where x is larger than 1, which means it's just a sum of even numbers, which has to be even. And then over here, it's just even numbers plus 1, because it's just the same thing as the first one, a string of binary followed by 0 plus 1, which just makes it equal to 2k plus 1. So first, we prove the base case of n equals 1. N equals 1 equals 1 in binary. And because this is our first case, it's unique. And now we make the strong inductive assumption, inductive hypothesis, it doesn't matter. So we assume that n equals 1, 2, all the way to 2k minus 1 can be expressed uniquely in binary to prove a 2k, or we can do the same to prove 2k plus 1. So if k is unique, then 2k and 2k plus 1 must also be unique. Because by strong induction, we don't only use it for all the terms. We only use it for the single k term, but because it contains all the terms, it will contain the k term. That's why we use strong induction instead of just regular induction. And because it's part of our assumption, then it must be unique, right? And then 2k is just k followed by 0 in binary, and 2k plus 1 is just k followed by 1 in binary. Does everyone understand? Which means by using 1, 2, all the way to 2k minus 1, we can get 2k and 2k plus 1. But is this sufficient to prove the problem? That every positive number can be expressed as a unique sum of distinct powers of 2? It is, right? Because after this, we just have 1, 2, 2k plus 1 to prove 2k plus 2 and 2k plus 3. So it is sufficient to prove all of this. So now we'll do these. Consider a sequence defined as d1 equals 1, d2 equals 2, d3 equals 3, and d n plus 3 equals d n plus 2 plus d n plus 1 plus dn for all positive integers n. Show that dn is smaller than 2 to the power of n. So it's basically just a 3-term Fibonacci. I'll give you guys 1 minute to try this problem. This time it's for bounding. So the inductive hypothesis would have to do something with bounding. Okay, so what would our base case be? Now we can't choose 1, right? Oh, as the largest number. Oh, it doesn't matter. Okay, we can choose base case 0. Oh, wait, no, never mind. Base case 1. So we know that d1 is smaller than 2 to the power of 1, which makes the base case true. And then after that, we suppose it's true for d2, d1, d2, d3, dot, 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 dk. So what would this mean? This means that all dk, all di for I equals 1, 2, 3, dot, 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 k are smaller than 2 to the power of 5. So this would mean for k plus 1, where dk plus 1 equals dk plus dk minus 1 plus dk minus 2. We know that dk is smaller than 2 to the k. dk minus 1 is smaller than 2 to the k minus 1. dk minus 2 is smaller than 2 to the k minus 2. We can replace these terms with 2 to the k, smaller than 2 to the k plus 2 to the k minus 1 plus 2 to the k minus 2. But what's special about this? This expression is equal to 2 to the k minus 2 times 1 plus 2 plus 4. But what is 1 plus 2 plus 4? That's 7, which is smaller than 8, right? So smaller than 2 to the k minus 2 times 2 to the 3, which is equal to 2 to the k plus 1. So that we've bounded it for the base case of d1. And by a strong induction, we assume it's true all the way to dk. And then we just, from our assumption, we can just replace the terms in the equation for dn plus 3, which we replace with dk plus 1, to show that it's smaller than 2 to the k plus 1. Oh, our base case needs multiple terms because we use this equation, the dn plus 3 equation. So we actually need to show the base case holds for d1, d2, and d3. in order to use n plus 3, which must be larger or equal to 4. d2 is equal to 2, which is smaller than 2 to the 2. And d3 equals 3, which is smaller than 2 to the 3. Yeah. And now we'll do the next exercise. Show that every integer n not equal 0 can be written in the form of n equals 2k times l, where k is a non-negative integer and l is an odd integer. So I won't give you guys any time to try this because you guys probably had solved it. Basically, we just prove a base case. I won't do that. But over here, if n is odd, then obviously we just do n equals l, right? But if n is even, this is where we use induction. So by strong induction, we assume for 1 through n minus 1. Right? But when we assume for 1 through n minus 1, this must contain n divided by 2 because n is even. Right? And if n over 2 is in this range, n is just 2 times that. So we can let n over 2 equal 2 to the k minus 1 times l. Then that means n equals 2 to the k times l, right? But is this unique? It is, right? Because any number that's n divided by 2 times 2 is just n. So it must be unique because it only applies to it. Okay, now we will move on to famous induction problems. So this is a pretty famous induction proof of the arithmetic mean, geometric mean inequality. So it's for the general form. Before we only proved it for 2 terms, but this proves it for all n terms for a positive integer. So the steps to proving it would first be to prove the powers of 2 work, which seems a bit absurd from what we've been doing so far, because so far we only did consecutive integers, but now we're going to powers of 2, which is basically just consecutive powers of 2. And then after that, we extend it to all positive integers by using a backwards step. Writing this on the slide would take too long, so I'll just go on the AOPS wiki. So before we proved the n equals 2 case, where we just use x minus y squared, and then we get must be larger than 0 to get x plus y over 2 is larger than or equal to square root of xy. And then now for powers of 2, suppose it works for like a sequence of n, of length n. Then we construct another one from x1, n plus 1 through to x2n using the same principle. And then when we add this and then divide by 2, we get x1 plus all the way plus x2n divided by 2n larger than or equal to the geometric mean for the first sequence of length n plus the geometric mean for the second sequence of length n, which is from n plus 1 to 2n, all divided by 2. And then we can just reapply the first principle, which is x plus y over 2 is larger than or equal to square root of xy for the nth root of x1 plus times all the way to xn plus nth root of xn plus 1 times all the way to x2n divided by 2 to get the 2nth root of x1 times all the way to x2n. So it's basically just combining inequalities. And because we basically set the original one to be x minus y equals 0 for equality, this one must have x1 equals dot 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 equals x2n for equality as well. So before we proved it is true for n equals 2, and now we proved it is true for all multiples of 2, right? So it's just true for all powers of 2 now. And this is the backward step, because before we had to prove it for all powers of 2, because powers of 2 can get arbitrarily large, which allows us to the backward step. Because if we just use the base case and then use the backward step, we'll end up at 0 pretty quickly. But then because powers of 2 can get arbitrarily large, we can just use the backward step to get to all positive integers. So the key step in the backward step is to let xn equal x1 plus dot 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 plus xn minus 1 divided by n minus 1. So why would this be the key step? Because it links n to n minus 1 by basically transforming the whole inequality to just the n minus 1 case. So let's see how it does that. So if you add from x1 to xn, because xn is now this expression, we would have just x1 times all the way, x1 plus all the way to xn minus 1 divided by n minus 1, which is the left-hand side of the n minus 1 inequality. And then now, in our geometric mean, we can't really do anything, right? Because we have an arithmetic mean within the geometric mean on the right-hand side of the AMGM expression. So this wouldn't help us because we can't really do anything with it at the moment. So we would just take everything to the power of n, which gets us the arithmetic mean of x1 through xn minus 1 to the power of n is larger than or equal to x1 times all the way to xn minus 1, but times x1 plus all the way to xn minus 1 divided by n minus 1, which is the same thing as this side, but to the power of 1 instead of to the power of n. So after we divide by this arithmetic mean on the right-hand side, we will get the left-hand side going to the power of n minus 1. And after that, we can take the n minus 1th root. And then after we take the n minus 1th root, we get that the arithmetic mean of x1 through xn minus 1 is larger than or equal to the n minus 1th root of x1 through n minus 1. So basically, we just reduced AMGM for n variables to AMGM for n minus 1 variables, which means that we can derive AMGM for n minus 1 variables if we have AMGM for n variables. And before we got powers of 2, right? So we can just choose basically infinity, and we can just work our way down. Does everyone understand? I feel like I might have lost some of you in that explanation. If you don't understand something, just tell me where you got lost, and then I'll try to explain it to you. Okay, no one's saying anything, so I'll just take it as if you guys all understand. But now I'll go through why the backward step works. Because by powers of 2, powers of 2, why would this be important in an induction? Because powers of 2 can get arbitrarily large. And another thing is that we want to prove this is true for all positive integers, which would be just finishing the problem if we could do that. But unfortunately, we can't directly prove that, which means we just go through powers of 2 first. Because this is not fully solving the problem, but then we can solve the problem by doing a backward step. So this can get us an arbitrarily large integer. And then backward step wouldn't work for a base case. Because if you think about it, our base case is only for 2. And our backward step goes from n back to n minus 1, right? And because it goes back from n to n minus 1, our 2 would go from 2 to 1 to 0, and then we can't go to negative 1. Okay, so now we'll do another famous case of induction for sum of powers of 2. So prove that for all positive integers n, 2 to the n minus 1 is the same thing as 1 plus 2 plus dot 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 plus 2 to the power of n minus 1. I'll give you guys 30 seconds to have a look at this problem. Okay, so our base case would obviously be n equals 0. Oh wait, no, n equals 1. Which would just be 1 equals 1, right? And then after that, we assume this is true. For some k. And then we want to get this to go to k plus 1. So how do we go from this expression for k to the next expression for k plus 1? So this side has a bunch of consecutive terms, but it has nothing to do with k. And this side has only 2 terms, and it has something to do with k. So we should look at the left-hand side. So for the left-hand side, it's 2 to the k minus 1. And we know that 2 to the k plus 1 is 2 to the k times 2, right? So we can just add 2k to both sides. And then now we have 2 to the k plus 1 equals, minus 1 equals 1 plus 2 plus dot 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 plus 2 to the k minus 1 plus 2 to the k, which is basically just the problem statement, but for k plus 1. Another way you could look at this problem would be to just look at it in binary. So what would the right-hand side look like in binary? It would look like 1, 1, 1, 1, 1, dot, dot, dot. And then what would the left-hand side look like in binary? It would look exactly the same because it's just 1 followed by a trail of zeros minus 1, right? But then if you minus 1 from 1 followed by a trail of zeros in binary, It just results in one less digit, but one followed by a bunch of ones. So it's intuitively the same. Okay, this is another famous consequence of induction. I don't know if this needs induction, but it's faster with induction. So it's a Fibonacci identity. Does everyone know what the Fibonacci sequence is? Okay, the Fibonacci sequence is basically the first term is equal to 1, second term is equal to 1, and all the terms after that is the sum of the two previous terms. So for our base case, we know that f1 equals, we need to prove that f1 equals f3 minus 1. If 1 is 1 equals, what's f3? That's just 1 plus 1, so it's 2 minus 1 equals 1. So that's obviously true. And then our inductive hypothesis would be to assume this is true for some k. F1 plus dot 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 plus Fk equals Fk plus 2 minus 1. So how do we extend this to Fk plus 1? We just add it on both sides, right? If we add it on both sides, we get Fk plus 2 plus Fk plus 1 on the right-hand side, which just simplifies to Fk plus 3 minus 1, which makes it obviously work for k plus 1. So now we've covered what induction is. We've covered strong induction. And we've also covered some famous induction problems. Now we'll do some of the handout problems since we finished the slides early. So the first problem is to show that n factorial is larger than 2 to the n for all positive integers n except for 1 and 2. So for all larger than or equal to 3. I made a typo. Oh wait, no, larger than 3. Sorry. So for all n larger than 3. So with induction, show that all n factorial is larger than 2 to the n. For positive integers, n is larger than 3. So can someone tell me a number we can use for the base case? Now that we have the bound n larger than 3. Tell me in chat. Okay, so basically since it has to be larger than 3, we can just try 4. We have 24 larger than 16, which is true. And then after that, we make the assumption for k, with k factorial larger than 2 to the k. And then because we know that k must be larger than 3, we can just multiply k plus 1 to both sides, which must be larger than 4, right? Which is obviously larger than 2. So we know that k plus 1 larger than 4. If we multiply out larger than 2, if we multiply k plus 1 to both sides of this inequality, we will get k plus 1 factorial larger than 2 to the k plus 1. So it's basically just a one-step induction problem. And then now let's do problem 4 since we have plenty of time. So I think this problem might be a bit hard for the handout, but then it's a fun problem. Oh, okay, let's just look at it on the handout. So the sequence A1 all the way to AN is a sequence that satisfies AI plus AJ is larger than or equal to AI plus J. Prove that for any positive integer n, we have that A1 over 1 plus A2 over 2 plus dot 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 plus AN over n is larger than or equal to AN. So this problem appeared in, I think, 1995 APMO. So it's not easy. Okay, so approaching this problem, how would we see that we should use induction? What would our main motivation for induction be? Because each term, we add on ak over k, right? But that's basically independent from the previous terms, apart from that term being something of a consecutive number. It's being related to consecutive numbers. And then also we have that positive integer n for any positive integer n, which basically just means for all positive integer n. So that's why we should use induction. So what would be the first step? It would be the base case. What's the base case? It's just a1 equals 1. a1 equals a1. So a1 is larger than or equal to a1. And then what would we assume after that? Oh wait, no, let me give you guys another hint. Since we have this huge expression, we can call the left-hand side Bn. So how would we use B, K to prove this is true? So basically now we're just bounding one sequence with another sequence. I'll give you guys 30 seconds to think about it. Okay. So if we let Bn equal this thing. Wait. I'll just cover it. Okay, let Bn equals this thing. How would we bound An by Bn? Because now, instead of bounding An by a ridiculous sum, we just bound An by bn. Right, so it's basically bounding a sequence by another sequence instead of bounding a sequence by a constant, which we did earlier. So what should we assume? We just assume the problem statement. So assume this is true for 1, 2, ... Okay. Let's make it n. Oh no, m minus 1. But if this is true for m minus 1, why would we use strong induction on it? We would do it because it's sum of b something larger than a. So if we sum all of them from n equals 1, n equals 2, ... n equals n minus 1, or k equals n minus 1, we will get sum of b's larger than or equal to sum of a's. Right? Because b1 plus b2, b1 larger than or equal to a1 is the case for 1. For 2, it would be b2 larger than or equal to a2. And then for n minus 1, it would be b n minus 1 larger than or equal to a n minus 1. Which gives us sum of b's from 1 all the way to n minus 1 is larger than or equal to sum of a's from 1 all the way to n minus 1. But then what is the sum of b's? The sum of b's is n minus 1 times a1 plus m minus 2 divided by 2 plus 8 times a2 plus ... plus n minus n minus 1, which is just the same thing as 1 times a n minus 1 divided by n minus 1. It's larger than or equal to the sum of a's, which is just a1 plus a2 plus ... plus an. But if we add a1 to both sides, if we add the sum of a's to both sides, we will get n times a1 plus n minus 1. Oh wait, no, plus n times a2 divided by 2 plus ... plus n times an minus 1 divided by n minus 1 larger than or equal to 2 times of this side, because we just added this onto both sides. Why is this significant? Because basically we get that the left-hand side now becomes n times b n minus 1. Right? But then what do we want? We want n times bn is larger than n times an, because that would just mean bn larger than or equal to an. So we can factorize this side into n times a1 plus a2 over 2 plus dot 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 plus an minus 1 divided by n minus 1 larger than or equal to 2 times this. 2 times a1 plus all the way to an. But what do we want? We want bn larger than or equal to an. So suppose it's true. Why would we suppose it even though we've already made the inductive hypothesis? We're already supposing two things. Wouldn't this be risky? It would be risky, but we do it to find out why bn is larger than or equal to an, because we don't know yet. So if we can combine this expression with what we have so far, maybe we can get a statement that links back to like the problem statement that tells us ai plus aj is larger than or equal to ai plus j, which we have not used so far. So that's why we make another assumption. So if we add bn to this side and an to this side, if we add both inequalities together, we get, it's the same thing as n times a1 plus a2 over 2 plus dot 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 plus, wait, no. Yeah, so plus dot 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 plus an over n. Oh, wait, no, if we add an to both sides, sorry. Okay, this is larger than, wait, I think I made a mistake. So don't suppose that and just add an to both sides. That's faster. So if we add an to both sides, we just get an plus this. But this is significant because everything inside the brackets is just bn. So we have n times bn larger than or equal to an plus 2 times a1 plus dot 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 plus an minus 1. So now the problem is nearly done. What's the time? Okay, we still have some time. So n times bn is larger than or equal to an plus 2, the sum from a1 all the way to an minus 1. How do we get that bn is larger than or equal to an? We want to link this to this. And we already have an an on this side, so we just need to prove 2 times a1 plus dot 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 plus an minus 1 is larger than or equal to n minus 1 times an. Because if we have this side is larger than or equal to n times an, and this side is n times bn, we have that n times bn is larger than or equal to this expression, which is n times an, which is larger than or equal to n times an. So how do we prove this? We just use the problem statement that tells us ai plus aj is larger than or equal to ai plus j. So how do we get an from ai plus j? Because we want this to be larger than or equal to an, right? Something times an. So clearly we want I plus j to equal n. We can just do pairing, right? So for I equals 1, we have j equals negative equals n minus 1 right? And then I equals 2. We have j equals n minus 2. Dot, dot, dot. We have I equals n minus 1, j equals 1. So how many terms is this of an? It's exactly n minus 1 an's. So if we do n minus 1 of these through I equals 1, j equals n minus 1, dot, 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 all the way I equals n minus 1, j equals 1, we get that this is larger than or equal to n minus 1 times an. So we can add this to our expression, n times an. So now we have that n times bn is larger than or equal to n times an. And then by taking n from both sides, we have that bn is larger than or equal to an, which solves the problem. So does anyone have any questions or anything that they don't understand? Okay, if not, then your next Mind and Z workshop will be on Monday, I think. It'll be on next Monday, so on the 29th of July with the geometry people. You guys can leave the meeting now. Thank you. Wait, how do I turn off record? Oh, you can leave the meeting now. Wait, do you know how to turn off record? Wait.